The solar system is mostly empty. Not somewhat empty. Not mostly full with some gaps. Mostly empty in the way that the word mostly doesn't even begin to cover it. The planets, all 8 of them, occupy a fraction so small of the solar system's total volume that if you removed them, you'd barely notice they were gone. The sun would still be there. The vast dark space between everything would still be there. And that space, that overwhelming cold, lightless space, is what the solar system actually is. But you were never shown that. Every educational image of the solar system compresses the distances so aggressively that the most important feature of our cosmic neighborhood disappears entirely. Not the planets, not the sun, the space between them. The enormous, dominant, crushing emptiness that separates every world from every other world is removed from the image because it doesn't fit. Because if it were shown honestly, the diagram would be mostly blank. The planets would be invisible specks, separated by expanses of white or black space that no textbook page could contain. So the diagram compresses. It brings the planets close together. It makes them look like neighbors. And that image, that emotionally comfortable, spatially dishonest image, is the one most of us carry through our lives as our mental map of where we live. The solar system is not a crowded place. It is not a neighborhood in any sense that word has ever meant. It is one star, 8 isolated worlds, and an almost incomprehensible amount of nothing. And the distance between those worlds is not just large in the way that the Pacific Ocean is large. It's large in a way that breaks intuition, that defeats our fastest machines, that imposes delays on the speed of light itself. Here is where this gets uncomfortable. Most people accept these facts as abstract knowledge. You nod along and think, yes, space is very large. I know, but there's a difference between knowing something and feeling the scale of it. And the scale of the solar system is something almost no one has actually felt. Because every image ever made of it has been lying, quietly and by necessity, about the one thing that matters most. This video is about that gap. Not the gap between planets, though we'll get to that. The gap between the solar system you think you live in and the one that actually exists. To feel the real scale, we have to start at the beginning. Not with the outer planets, not with the asteroid belt, not even with Mars. We have to start with the closest world to Earth. The one that looks so near it seems almost within reach. Because even the moon is farther than it looks. And if the moon surprises you, Mars is going to change something in the way you see all of this. The moon is the closest major body to Earth. On a clear night, you can see craters with a decent pair of binoculars. You can watch it move across the sky over the course of hours. It is, by every visual measure, the most present and immediate thing in the sky after the sun. It dominates the night. It's been a navigation tool, a calendar, a religious symbol, a source of wonder for our species for as long as we've been looking up. It is also, by the standards of anything we've ever tried to do in space, terrifyingly far away. The average distance from Earth to the moon is about 384,000 kilometers. That number probably doesn't register as anything alarming. Let's try to make it register. If you could drive to the moon at a typical highway speed, say 100 kilometers per hour, without stopping, without sleeping, just continuous unbroken driving across empty space, the trip would take you roughly 160 days. Not hours, days. Over 5 months of non-stop driving. To reach the nearest thing in the solar system. The object you can see without a telescope from your backyard on any clear night. Or think about it this way. The Apollo missions, the most impressive achievement in the history of human transportation, took about 3.5 days to reach the moon. 3.5 days traveling in a spacecraft, moving at speeds no commercial aircraft has ever approached. The lunar transit velocity on Apollo missions was roughly 3,900 kilometers per hour. At that pace, you could cross the continental United States in less than an hour. And it still took 3.5 days to reach the moon. Light does it in 1.3 seconds, which tells you something about how far it is, because light is fast in a way that makes anything humans have ever built look stationary by comparison. Here's a comparison that might make the moon's distance feel more physical. If you took all the other planets in the solar system, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and lined them up side by side, their combined diameters would fit into the Earth-Moon gap. Not just barely. They'd fit with room to spare. Every planet in the solar system except Earth can be slotted into the distance between Earth and the Moon when measured by their diameters. Shoulder to shoulder. The gap is that wide, and the Moon is the close one. This is the first lesson in solar system scale, and it's a disorienting one. The object that defines our night sky. The object so close we sent 12 human beings to walk on its surface. The object that causes our tides and stabilizes our axial tilt. That object is already separated from us by a distance that defies the intuition the night sky gives us. It looks nearby. It is not nearby. The visual impression it creates is one of the most reliable deceptions in all of human experience. Now here's the deeper implication. If the Moon is already far in this way, if even our most immediate neighbor requires 3 days of rocket travel and reveals itself, under scrutiny, to be separated from us by a gap large enough to swallow 7 planets, then what does that say about the rest of the solar system? What does it say about Mars? Mars is the planet that captures human imagination more than any other. It's the destination, the second home, the next chapter in the human story. It has surface features we can photograph in detail. It has weather. It has seasons. It has a day that lasts almost exactly as long as an Earth day. It has mountains and valleys and dried riverbeds that tell a story about a world that once had liquid water on its surface. It's the planet we talk about visiting when we talk about the future of our species. It's also not nearby, not even close to nearby. The tricky part about Mars is that the answer to how far away is it changes depending on when you ask. Earth and Mars both orbit the Sun, but they orbit at different speeds and at different distances. Earth takes 365 days to complete one orbit. Mars takes about 687 days, so they're constantly moving relative to each other, sometimes swinging close on the same side of the Sun, sometimes drifting to opposite sides with the Sun sitting in the gap between them. At closest approach, what astronomers call opposition, Mars can be roughly 54 million kilometers from Earth. That sounds like it should be a manageable number. It isn't. 54 million kilometers is more than 140 times the distance from Earth to the Moon. Remember how far the Moon was? Multiply that by 140, and that's the close case. At its farthest, when Earth and Mars are on opposite sides of the Sun, the gap expands to over 400 million kilometers. Same 2 planets, same solar system, but the distance between them varies by a factor of roughly 7, depending on where they happen to be in their orbits. This is why Mars missions have specific launch windows. You can't leave for Mars whenever you feel ready. The geometry of the orbits only cooperates for a period of a few weeks every 2 years, when the alignment makes a fuel-efficient trajectory possible. Miss that window and you wait another 26 months. And even during the window, you're not flying directly at Mars. You're flying along a curved arc, a transfer orbit, aimed at where Mars will be when your spacecraft arrives months later. Not where it is now, where it will be. Because by the time you get there, Mars has moved. The planet you aimed at is already gone. Think about what that means as a travel challenge. You're launching from a moving platform, Earth, orbiting the Sun at about 107,000 kilometers per hour. You're aiming at a moving target, Mars, orbiting at about 87,000 kilometers per hour, and the distance between the two keeps changing throughout the journey. Getting to Mars isn't like sailing across a wide ocean to a distant shore. It's like trying to intercept a moving island from a moving shore, both of which are simultaneously orbiting a central fire, during a brief window when the geometry of the situation makes the interception mathematically possible. The fastest Mars missions have taken about 7 months to complete the transit. 7 months of travel in a spacecraft through the interplanetary void to cover a distance that varies but averages somewhere around 225 million kilometers depending on the orbital phase. 7 months in a metal vessel where radiation exposure is a serious health concern, where every system has to function perfectly without the option of a repair crew reaching you from Earth, and where any emergency that develops will be managed by a crew in communication with Earth, subject to a radio delay that grows and shrinks throughout the mission, but can reach up to around 24 minutes each way. 24 minutes one way. Nearly 50 minutes for a single back and forth exchange. If you're on Mars and something goes wrong and you send an emergency transmission to Earth, the people who could theoretically help you won't know something happened for 24 minutes. Their response, if they send one immediately, takes another 24 minutes to reach you. Whatever you're dealing with it alone for at least the first 48 minutes, on the best day, when the orbits happen to align in your favor. This is Mars. This is the planet we talk about as humanity's next destination. The one that gets described in popular discourse as almost within reach, as something we could visit within this generation if we summoned the will and the resources. And everything I've just described is the close, optimistic version of the situation. The numbers at closest approach, the fastest transit times, the most favorable communication delays. The uncomfortable truth is this: even our nearest, most talked about planetary neighbor is not nearby in any human sense. It's not nearby in any sense that the word neighboring has ever carried. It's a distant, isolated world moving through its own orbit around the sun, reachable only at specific windows in a cycle that repeats every 2 years, requiring months of travel through conditions no human body was designed to endure. And Mars is the easy one. At some point in your education, you were given a specific mental image of the solar system. 8 planets arranged in order from the sun, spread out to the right of a glowing yellow circle, each labeled, each at roughly the same visual interval from its neighbors. Mercury close to the sun, then Venus, then Earth with its moon, then Mars, then Jupiter, enormous and banded, then Saturn with its rings, then Uranus tilted sideways, then Neptune blue and distant at the far end. That image is not the solar system. It's a logo for the solar system. A symbol. A shorthand that communicates which planets exist and roughly what order they sit in, but which has no relationship to where those planets actually are in space at any given moment. The planets don't orbit in a line. They orbit in ellipses, slightly oval paths, at different distances from the sun, and they move along those paths at different speeds. At any moment, some planets are on the same side of the sun as Earth. Some are on the opposite side, with the full width of the solar system between them and us. Some are above or below the plane that most of the other planets occupy. The three-dimensional arrangement of the planets is always different, always in motion, and bears no resemblance to the neat row in the diagram. When Jupiter and Earth are on the same side of the sun, the distance between them can be somewhere around 590 million kilometers. When they're on opposite sides, that distance grows to over 960 million kilometers. That's not a minor variation. That's a difference of nearly 400 million kilometers between the closest and farthest possible positions. For the same 2 planets, in the same solar system, at different points in their orbits. The diagram doesn't hint at this. The diagram suggests that Jupiter is always right over there, at a fixed and knowable distance just past the asteroid belt. It isn't. Nothing in the solar system sits at a fixed distance from anything else. Every distance is a snapshot of a system in constant motion, and the snapshots vary dramatically depending on when you take them. There's something else the lineup hides that matters even more than the varying distances: the enormous spans of empty space between the planets. In the diagram, the visual intervals between Mercury and Venus, between Venus and Earth, between Earth and Mars, these look roughly comparable. They look like hops. In reality, the gaps grow dramatically as you move outward. The distance from Earth to Mars at closest approach is roughly 54 million kilometers. The distance from Mars to Jupiter at closest approach is over 550 million kilometers. That's 10 times larger than the Earth-Mars gap, and the diagram doesn't convey that ratio at all. It can't, not without becoming unreadable. The distance from Jupiter to Saturn is even larger, and from Saturn to Uranus, larger still. Each step outward in the solar system covers more ground than all the steps before it combined, in a rough geometric progression that the diagram compresses into uniform visual spacing. This compression changes the emotional meaning of the solar system. It makes the outer planets feel like they're roughly as far away as the inner planets, just in a different neighborhood. They're not. They're separated from the inner solar system by distances that dwarf the distances between the inner planets, and separated from each other by distances that dwarf those. The solar system doesn't scale like a page, it scales like a universe unto itself. The lineup is comfortable, the lineup is learnable, the lineup is the version of the solar system that fits in a textbook and a child's mind and a bedroom poster. But it is not the solar system. It is a symbol standing in for a reality too large to show honestly. And the gap between the symbol and the reality becomes undeniable when you reach Jupiter. Jupiter is where solar system scale stops being abstract and starts being visceral. At closest approach, Jupiter is about 590 million kilometers from Earth. At farthest, over 960 million kilometers. Call it roughly 750 million kilometers on an average day, a number that doesn't carry any weight until you put it next to something that does. Light travels at about 300,000 kilometers per second. It's the fastest thing that exists. Nothing in the known universe moves faster. And a signal traveling at the speed of light, a radio transmission, a command from mission control, a data stream from a spacecraft, takes between 33 and 53 minutes to travel from Earth to Jupiter, depending on where Jupiter sits in its orbit. Think about what that means practically. When the Juno spacecraft arrived at Jupiter in July 2016, after traveling for almost 5 years, mission controllers at NASA's Jet Propulsion Laboratory had to watch the orbital insertion burn unfold in near complete helplessness. The signal delay was about 48 minutes each way. By the time Juno transmitted its first signal confirming the burn had started, the burn was already long over. By the time the confirmation arrived on Earth, the outcome, success or failure, had already been determined 48 minutes earlier, 500 million kilometers away, with no possibility of human intervention. The scientists in the control room were not controlling Juno in any real-time sense. They were watching a recording of an event that had already resolved. Juno fired its engine, completed its burn, and entered Jupiter's orbit entirely on its own, executing a pre-programmed sequence that had been loaded weeks before, because the distance made real-time control physically impossible. That's the relationship between Earth and Jupiter, not the comfortable, almost neighbor suggested by the diagram. A distant autonomous relationship defined by signal delays that turn mission control into mission observation. Now think about how Juno got there. It launched in August 2011. It flew past Earth in 2013 to pick up a gravity assist, looping back around our planet to steal a bit of orbital energy and add it to its own velocity. It reached Jupiter in July 2016. Nearly 5 years of travel at speeds that sound extraordinary. At various points in its trajectory, Juno moved at over 200,000 kilometers per hour. Faster than almost any object humans have ever launched. 5 years. To reach a planet that is, in the diagram, just past the asteroid belt. And Jupiter is not a dim, forgettable destination. It's the largest planet in the solar system. Its mass exceeds the combined mass of all of the other planets put together, more than twice over. Its Great Red Spot is a storm that has been raging continuously for centuries, large enough to contain the entire Earth inside it. Its moon Io is the most volcanically active body in the solar system. Its moon Europa may harbour a liquid ocean beneath its icy crust, one of the most compelling candidates for extraterrestrial life anywhere we know of. Ganymede, another of its moons, is larger than the planet Mercury. These are not peripheral details. Jupiter and its moons constitute a miniature solar system within our own, with extraordinary complexity and possibly extraordinary significance. And it requires 5 years of spacecraft travel and a 48-minute communication delay just to visit. Here's the part that really breaks the scale. Jupiter is only about a third of the way across the planetary zone of the solar system. Neptune, the outermost planet, is about 6 times farther from the Sun than Jupiter. If getting to Jupiter takes 5 years at spacecraft speeds, the outer solar system requires the kind of patience that borders on the geological. And this is where the solar system stops being merely large and starts being something else entirely. There's a shift that happens somewhere in the outer solar system. It happens gradually, but once you feel it, you don't forget it. In the inner solar system, distance feels like a practical challenge. Difficult, expensive, technically demanding, but a challenge in the category of things humans have at least begun to address. We've sent rovers to Mars, we've sent orbiters to Jupiter. These things happened. They took years of effort and decades of planning, but they happened. As you move towards Saturn, Uranus, and Neptune, the nature of the distance changes. It stops feeling like an engineering problem and starts feeling like a statement about the limits of human timescales. The distances are no longer just large. They're large in a way that stretches past careers, past funding cycles, past institutional memory. Saturn sits about 1.4 billion kilometers from the Sun. That's almost 10 times the Earth-Sun distance. A signal traveling at the speed of light takes about 80 minutes to reach Saturn from Earth, over an hour, one way, for light. The Cassini spacecraft orbited Saturn from 2004 to 2017, returning some of the most scientifically valuable data in the history of planetary exploration. Images of Saturn's rings in extraordinary detail, close flybys of Titan's methane lakes, the discovery of water vapor geysers erupting from the surface of Enceladus, 13 years of orbital science, and every piece of data it collected, every image it sent, every instrument reading it transmitted, arrived on Earth over an hour after it was recorded. Every command sent to Cassini took over an hour to arrive. The spacecraft operated in a perpetual time lag, a permanent asynchrony between the machine and the people who designed it. Cassini launched in 1997. It reached Saturn in 2004. 7 years of transit, Uranus is farther, about 2.7 billion kilometers from the Sun on average. A light signal takes roughly 2.5 hours to travel from Earth to Uranus. We have sent exactly one spacecraft to Uranus in all of human history, Voyager 2, which launched in 1977 and flew past Uranus in January 1986. 9 years of travel for a flyby that lasted hours. The images Voyager 2 returned from Uranus took 2.5 hours to reach Earth at the speed of light. For decades, those flyby images were the best views of Uranus humanity had ever obtained, and they were captured by a spacecraft that spent 9 years crossing the solar system for a visit that was over before most people heard it had begun. Neptune is the outermost planet, sitting about 4.5 billion kilometers from the Sun. Sunlight takes roughly 4 hours and 20 minutes to reach it. When you think about what that means, that a photon leaving the Sun, traveling at the maximum speed in anything in the universe can travel, takes 4.5 hours to reach the outermost planet in our solar system. The scale starts to feel like something other than a number. It starts to feel like a physical reality, a constraint, a wall. From Neptune, the Sun is still visible to the naked eye, still the brightest point in the sky, but it's a point, a very bright star rather than the overwhelming presence that defines our sky from Earth. The warmth it provides at that distance is so diluted about 900 times weaker than what we receive on Earth, that it has almost no meaningful effect on temperature. Neptune sits at an average temperature of about minus 200 degrees Celsius. Not because there's no sun, because the sun is too far away to matter. Voyager 2 flew past Neptune in August 1989. It had launched 12 years earlier in August 1977. 12 years of continuous travel to reach the outermost planet. Signals from the Neptune encounter took 4 hours to reach Earth at the speed of light. When scientists saw the images arrive, they were looking at data that was 4 hours old, data from a machine 12 years away. Here's a thought that keeps resonating the longer you look at these numbers. The time delays imposed by these distances aren't incidental inconveniences. They're the fundamental condition of the outer solar system. They mean that any mission to the outer planets is inherently a mission in which the people who designed the spacecraft and the people who receive its data are operating in different time zones. Not by hours in the human sense, but by hours at the speed of light. The machine and the mission team exist in a permanent, physics-imposed asynchrony. At some point, distance stops feeling like space and starts feeling like abandonment. A spacecraft sent to Neptune doesn't feel like an explorer sailing to a distant country and sending back letters. It feels like something released into a darkness from which contact, real contact, timely contact, meaningful contact, becomes gradually impossible. The data still arrives. The images are still extraordinary. But the relationship between the machine and the people who built it becomes, over time, something closer to archaeology than engineering. You're not directing something. You're receiving transmissions from something that made its own decisions hours ago. And none of this accounts for what lies beyond Neptune. Stop thinking about the destinations for a moment. Think about what's between them. When a spacecraft travels from Earth to Mars, or from Earth to Jupiter, or from Jupiter to Saturn, it does not travel along a road. It does not move through any medium the way a ship moves through water or an aircraft moves through air. It falls through a vacuum, guided by gravity and mathematics, across hundreds of millions or billions of kilometers of what is, for all practical purposes, almost nothing. But not quite nothing. Interplanetary space has content. It's permeated by the solar wind, a constant flow of charged particles, or T, mostly protons and electrons, streaming outward from the sun in every direction at speeds of 400 to 800 kilometers per second. These particles carry the sun's magnetic field with them, threading it through the entire solar system in a vast, dynamic structure called the heliosphere. There are dust particles in interplanetary space, fragments from comet tails, debris from asteroid collisions, primordial material left over from the formation of the solar system 4.5 billion years ago. There are micrometeoroids, some smaller than grains of sand, drifting in slow orbital paths. There is radiation, high-energy particles from the sun and from outside the solar system, cosmic rays that penetrate almost anything and pose genuine health risks to any living organism making a long interplanetary journey. So interplanetary space is not nothing. It's a real physical environment with real properties. Spacecraft are affected by the solar wind. Their instruments respond to the radiation. Their trajectories are subtly shaped by the pressure of sunlight itself. But here's what it doesn't contain. Any of the things that make an environment habitable or even functional for human beings or human machines in the ways we usually mean. No air, no pressure, no temperature gradient that could warm you, no medium to carry sound, no surface to push against, no nearby object to provide any visual reference for where you are or how fast you're moving. The best vacuum chambers ever built on Earth, the ones used in particle physics experiments, contain about 10 trillion molecules per cubic meter. Interplanetary space contains a tiny fraction of that. Imagine floating midway between Earth and Mars, not in a spacecraft, just suspended in space, in this environment, if such a thing were possible. What do you experience? Silence first. Not the silence of a quiet room, where you can still hear your own breathing and heartbeat and the faint ambient hum of the world around you. Silence in the absolute physical sense, no medium to carry vibration of any kind. Sound requires molecules, and there are almost no molecules. Whatever is happening around you, the solar wind streaming past, any micrometeoroids drifting by, none of it produces any sound in the environment you're in. It is as physically quiet as it is possible for an environment to be. Darkness everywhere except where you're not looking at the sun. And the sun, even from roughly halfway to Mars, looks different than it does from Earth. Still overwhelmingly bright. Still dangerous to look at directly. But smaller, more distant, more like what it is, a star, and less like the dominant feature of an inhabited sky. In every direction except the sun, black. No horizon, no ground, no ceiling, no object within millions of kilometers in any direction except the two planets you're between, and they're so far away that they appear as points of light. Earth behind you would look like a bright blue star. Mars ahead would be a reddish point, dim against the black. This environment, this interplanetary void, is what every spacecraft ever sent to another planet has to cross. What every astronaut sent to Mars would have to survive crossing, for months, in a vehicle small enough to be dwarfed by the distances involved. What every radio signal and every camera image has to travel through at the speed of light, for minutes or hours before arriving. The void between planets is not a road. It doesn't feel like a space between places. It feels like its own place. An enormous, undifferentiated environment defined entirely by absence. No surface, no warmth, no sound, no color except the pinpoints of light that tell you where you are relative to worlds that are still impossibly far away. And a spacecraft crossing this void doesn't sail through it. It falls. It falls in a carefully calculated arc, trading gravity from one body for gravity from another, traveling at speeds that would be extraordinary on Earth, but feel almost meditative against the scale of the distances involved. The void between planets is the real solar system, not the planets themselves, as remarkable as they are. The space between them, the overwhelming, dominant, silent, dark environment that a spacecraft spends years crossing, that is the true character of the place we call home. We like to describe spacecraft speeds in ways that emphasize how fast they are, and by any terrestrial measure they are fast. Remarkably, impressively, mind-bendingly fast. The Parker Solar Probe, currently the fastest human-made object ever built, has reached speeds exceeding 600,000 kilometers per hour on its closest approaches to the Sun. At that velocity, it could cross the continental United States in about 15 seconds. It would travel from Earth to the Moon in less than 40 minutes. It is the pinnacle of human engineering for speed, the absolute fastest we have ever sent anything. At Parker Solar Probe's top speed, the trip from Earth to Mars at closest approach would take roughly 3 weeks. The trip to Jupiter would take about 4 to 5 months. The trip to Neptune would take over 4 years. 4 years to reach the outermost planet, at the maximum speed we've ever achieved. And Parker Solar Probe only reaches those speeds during its closed solar passes. It can't maintain that velocity across an interplanetary journey. In practice, missions to the outer solar system travel much more slowly, using the gravity of planets along the way to build speed incrementally. New Horizons is the most instructive example. Launched in January 2006, it was at the time the fastest spacecraft ever launched directly from Earth. It left our planet moving fast enough to escape Earth's gravity almost immediately. No need to orbit first. It flew past Jupiter in February 2007, using that planet's enormous gravity to add speed and deflect its trajectory toward the outer solar system. It reached Pluto in July 2015, 9.5 years, to cover a distance that light crosses in about 4.25 hours, 9.5 years of travel versus 4.25 hours at the speed of light. The fastest human spacecraft versus the fastest possible messenger. That ratio, roughly 20,000 to 1, is the gap between what physics permits and what human engineering currently achieves when it comes to crossing solar system distances. Voyager 1 provides an even more humbling perspective. Launched in September 1977, Voyager 1 is currently the most distant human-made object in existence. After over 4 decades of continuous travel through the solar system and into interstellar space, it has covered approximately 23 billion kilometers. It is, without question, farther from Earth than anything humanity has ever sent. The signal returning from it takes about 22 hours to reach Earth at the speed of light. 22 hours at light speed. And in 4+ decades of travel, Voyager 1 has covered a distance that is, in the context of the full solar system, including the outer Kuiper Belt and the theorized Oort cloud, a relatively short distance from the Sun. The solar system's full gravitational territory may extend out to 100,000 astronomical units or more. Voyager 1 has covered about 160 astronomical units. It has barely crossed the threshold of the neighborhood. What Voyager's trajectory reveals is not a failure of ambition or engineering. It reveals something more fundamental. The solar system is calibrated to a timescale that human civilization has not yet come to terms with. The missions that have explored it, Voyager, Cassini, Juno, New Horizons, Pioneer, are extraordinary achievements, requiring decades of planning and years or decades of execution. The scientists who designed these missions have often retired or died before the missions completed their primary science objectives. Cassini's mission at Saturn lasted 13 years. The scientists who led its design in the early 1990s were receiving its final data transmissions in 2017. A quarter of a century passed between the conception of a mission and its conclusion. And Saturn is not even close to the outer edge of the solar system. Our machines are fast on Earth. In the solar system, they crawl. And the solar system, it turns out, extends far beyond the 8 planets the crawling machines have been sent to visit. Here's something that rarely gets mentioned in conversations about the solar system. The solar system doesn't end at Neptune. It doesn't end at Neptune in the way that a city doesn't end at the last famous building you've heard of. There's more. A lot more. And it changes the scale of everything discussed so far. Just beyond Neptune, beginning at about 30 astronomical units from the Sun, 1 astronomical unit being the Earth-Sun distance, about 150 million kilometers, lies the Kuiper Belt. It's a broad, flattened region of space containing thousands of icy objects, the frozen remnants of the early solar system, bodies that never coalesced into full planets but have been orbiting the Sun for billions of years. Pluto is the most famous resident of the Kuiper Belt. It sits at about 39 astronomical units from the Sun. Light takes over 5 hours to reach it. New Horizons reached Pluto in 2015 after 9.5 years of travel. When it did, the images it returned showed a world of unexpected complexity. Mountain ranges made of water ice, vast plains of frozen nitrogen, a distinctive heart-shaped feature that became one of the most recognizable images of the space age. And Pluto sits at the inner edge of the Kuiper Belt. Beyond Pluto, the belt continues, scattered with other dwarf planets and smaller bodies, out to perhaps 50 astronomical units from the Sun. Beyond the Kuiper Belt lies the scattered disk, a population of objects on highly elliptical, steeply inclined orbits that take them far from the main plane of the solar system. Some of these objects swing out to hundreds of astronomical units before looping back. Sedna, a reddish dwarf planet discovered in 2003, has an orbit that takes it roughly 1,000 astronomical units from the Sun at its most distant point. 1,000 times the Earth-Sun distance. Light takes over 5 days to cover that distance, but even the scattered disk isn't the edge. Not by a long way. The heliosphere, the bubble of solar wind and solar magnetic field inflated by the Sun into the surrounding interstellar space, extends to about 120 to 130 astronomical units. That's where Voyager 1 crossed in around 2012 into the region astronomers call interstellar space. But the Sun's gravity still dominates out to vastly greater distances. Theoretically, surrounding all of this, at distances estimated between perhaps 2,000 and 100,000 astronomical units from the Sun, lies the Oort cloud. The Oort cloud is a vast, roughly spherical shell of icy bodies, the source of the long-period comets that occasionally fall into the inner solar system on orbits that take thousands of years to complete. We've never observed it directly. We infer its existence from the behavior of comets and the physics of planetary formation. No spacecraft in the history of space exploration has come anywhere near it. The nearest star to the Sun, Proxima Centauri, is about 268,000 astronomical units away. If the Oort cloud extends to 100,000 astronomical units, its outer edge would be roughly a third of the way to the nearest star. Let that sit for a moment. The outer edge of our solar system, the full extent of the territory the Sun holds in gravitational bondage, reaches about a third of the way to the next star. The Sun's kingdom is that large. Now look at the standard solar system diagram. Find Neptune at the outer edge. Understand that what lies beyond Neptune in physical reality is a territory almost incomprehensibly larger than everything inside it. Virtually unexplored, virtually unmapped, virtually unreachable with current technology. And understand that the 8 named planets, the bright landmarks of the diagram, are just the inner layer of a domain that stretches almost to the doorstep of the next stellar system. The planets are not the solar system. They are the most visible fraction of the solar system, lit up by proximity to the Sun, close enough to study in detail. The dark territories beyond them are ancient, vast, and almost entirely unknown. The 8 planets are the bright stones near the center of a dark empire whose true extent has barely been grasped. At this point, it's worth being honest about something. The people who made the solar system diagrams, the educators, the illustrators, the textbook authors, the documentary producers, were not trying to deceive anyone. They were solving an impossible design problem with the best tools available to them. And the solution they arrived at was, for most educational purposes, entirely reasonable. Here's the problem. If you try to draw the solar system with the planets at their correct sizes and at their correct distances from the Sun, simultaneously in the same image, you immediately run into a wall. Try it on paper. Draw the Sun as a circle 1 centimeter in diameter. At that scale, Earth's diameter would be about 0.09 millimeters. A dot you'd need a magnifying glass to see. And Earth's orbit would be placed about 107 centimeters away from the center of your Sun. Fine. But Neptune? At the same scale, Neptune's orbit would be about 32 meters away. You'd need a room the size of a basketball court to fit the Sun and Neptune on the same diagram, and at that scale, every planet would be invisibly small. Push the other way. Draw Neptune's orbit small enough to fit on a page, say a circle 20 centimeters across. Now the Sun is a dot 0.3 millimeters across. Earth's orbit is 3.3 millimeters from the center. Earth itself is microscopic. Jupiter, the largest planet, is still too small to see without assistance. There is no scale at which both the planets and their orbital distances are visible to the naked eye in the same image. It's a geometric impossibility. The distances are simply too much larger than the planet sizes for any normal representational constraint to accommodate both truthfully. So the diagram compromises. It shows the planets at sizes large enough to be visible and labeled. It shows their orbital sequence. It might include a scale bar noting that distances are not to scale, and it arranges them at intervals that look reasonable on a page, even though those intervals bear no relationship to the actual ratios. The diagram is useful. The intuition it gives you is wrong. This is not a minor failure mode. The intuition it creates, that the solar system is a compact, navigable, populated place with worlds at roughly uniform intervals, is so persistent and so embedded that even people who know intellectually that the distances are enormous, continue to feel the solar system as something small. We correct the facts without correcting the feeling. And the feeling is what drives the intuitions. The sense that Mars is practically next door, that Jupiter is just a bit farther, that the outer solar system is somehow reachable in the way that the inner solar system might eventually be reachable. Some designers have tried to solve this problem in other ways. There are scrollable websites that show the solar system to true scale, where you spend several minutes scrolling through darkness before the first planet appears. There have been physical demonstrations in parking lots and parks where scale models of the solar system are placed at accurate distances, where the sun might be a grapefruit and Earth a tiny bead almost 30 meters away, and Neptune is somewhere out of sight over a kilometer distant. These experiences are powerful precisely because they feel so different from the diagram. They make the emptiness physical. They make the isolation felt. But those aren't the images most people encounter. Most people encounter the poster, the textbook page, the spinning animated graphic. Most people build their emotional map of the solar system from those compressed images. And that map stays with them. The diagram is a design solution to a genuine design problem. But every design solution carries consequences, and the consequence of this one is a civilization that knows the solar system is large without ever having felt what large means in this context. Bring everything together and try to see the solar system as a real physical object. Not as a diagram, not as an image, as a thing that exists in space, one star at the center. A sphere of plasma about 1.4 million kilometers in diameter, converting hydrogen into helium in reactions so energetic that the light and heat they produce travel across billions of kilometers of space to warm a small, rocky world orbiting at the right distance. Around this star, held in gravitational orbits, 8 planets ranging from the rocky inner worlds to the enormous gas and ice giants of the outer system. These 8 planets contain essentially all the solid and gaseous mass in the solar system that isn't the sun. They are the places, the named destinations, the worlds with atmospheres and surfaces and moons. They are the entire cast of characters in every future story about human expansion beyond Earth, and they occupy, proportionally, almost nothing. If you compressed the entire solar system, sun, all 8 planets, all their moons, the asteroid belt, the Kuiper Belt, every comet and rock and particle of dust, to the size of a basketball, the planets themselves would be far below the threshold of visibility. Not just small, invisible. The solar system, at basketball scale, would be a basketball-sized volume of dark space with a microscopic point of light in the center and several points too small to resolve anywhere near it. Most of the solar system's volume is the space between these objects. Dark, cold, sparse space threaded with the solar wind and the sun's magnetic field, but functionally empty of anything a human being could stand on, shelter in, breathe, or interact with. Now think about what it actually means to live here. Earth is not embedded in a rich, populated environment. Earth is a small, rocky world orbiting a medium-sized star, separated from the nearest other planet by tens of millions of kilometers at minimum, separated from the nearest other star by about 40 trillion kilometers. The planets in our solar system are not a neighborhood. They are isolated outposts, each on its own orbital track, each separated from the others by a void that takes months of spacecraft travel to cross. The Moon, the closest world to Earth, requires 3 days of rocket travel. Mars requires 7 months, Jupiter requires 5 years, Neptune required 12 years. And those numbers assume you leave at exactly the right moment, in exactly the right direction, following a trajectory that requires years of mathematical planning to derive. This is the environment our species is contemplating when it talks about becoming multiplanetary, not a commuter trip to a nearby settlement. A months-long voyage through interplanetary vacuum to a world where the communication delay to Earth ranges from several minutes to nearly an hour each way, where resupply missions take additional months to arrive, where the margin for error is near zero and the distance to any possible rescue is measured in hundreds of millions of kilometers. The existential weight of this is hard to absorb all at once. We know the solar system is large, we repeat it as a fact, but knowing it and feeling it are different, and the feeling is what shapes behavior, ambition, and the quiet background assumptions we make about where we are and what's reachable. The real solar system is not a cozy home. It is not a warm, navigable, populated place. It is one star surrounded by isolated worlds in an ocean of dark, separated by distances that our fastest machines struggle to cross in years and decades, communicating with each other at the speed of light with delays measured in minutes and hours. The planets are real. Their complexity and their potential are real. But the closeness is not. The closeness was always the diagram. Earth is not at the center of a neighborhood. Earth is a single inhabited point in a gravitational system too large to traverse in any human lifetime using any technology we currently possess. Our neighbors are not next door. They are not next month. They are, in some cases, not reachable within a human career. The solar system is our home. But it is not small. It is not warm. It is not close. It is a dark system of isolated worlds circling one fire, separated by voids that swallow our fastest machines and our most urgent signals alike, extending into outer territories that no spacecraft has ever visited, and that may never be visited by anything we send from this planet in this century. That is where we live. That is the address. And it looks nothing like the diagram. Come back to where this started. The solar system is mostly empty, not somewhat empty, not mostly full with some gaps, mostly empty, in the way that the word mostly is doing almost no work at all when you apply it honestly. The volume of space occupied by the planets is a rounding error in the total volume of the solar system. The space between things is not the background, it is the content. The void between Jupiter and Saturn is not a gap between two interesting features. It is itself the dominant feature. Hundreds of millions of kilometers of near vacuum, solar wind, and darkness through which any spacecraft transiting between those two worlds would spend years falling. Everything else in this video has been describing the same thing from different angles. The moon's surprising distance, Mars's unreachable movingness, Jupiter's 5-year transit time, Neptune's 4.5-hour light delay, Voyager's 47 years of travel to the edge of the heliosphere, the Oort cloud's unfathomable extent. All of these are descriptions of the same fundamental reality. The solar system is built from distance. Distance is its dominant property. The planets are the exception. Brief concentrations of matter at vast intervals in an otherwise empty gravitational field. The picture most of us carry of the solar system, the ordered, compact, navigable diagram of 8 planets in a row, compresses this reality until its emotional meaning changes entirely. In the diagram, the solar system feels inhabited. It feels like a place with geography. It feels like a territory humanity could reasonably explore and eventually occupy. That feeling is not dishonest in its origin. The diagram had to compress the distances to fit the page, and compression was the only tool available. But the psychological consequence of the compression is a population of people who live in one of the most remote and isolated environments in the known universe, and don't quite feel the weight of that. Who talk about Mars missions the way they talk about Antarctic expeditions? Difficult, expensive, demanding, but essentially in the same category as other challenging human journeys. Who talk about the outer solar system as though it's a territory awaiting exploration in the near term, rather than a region whose nearest planets require longer travel times than any sea voyage in the history of our species, multiplied by several orders of magnitude. Here's what's actually true. A radio signal sent from Earth to Neptune right now will take about 4.5 hours to arrive. Any reply takes another 4.5 hours to return. 9 hours for a single exchange at the speed of light to and from the outermost planet. The fastest we've ever moved anything is roughly 600,000 kilometers per hour. At that speed, the trip to Neptune would take over 4 years, and the Parker Solar Probe only reaches those speeds in brief bursts near the Sun, not across the vast interplanetary distances a Neptune mission would require. These aren't numbers that should terrify us. They're numbers that should humble us and properly inform the ambitions we build. Exploring the solar system is one of the great challenges of the coming centuries, and the fact that it's difficult is not a reason to stop. It's a reason to understand what we're attempting with clear eyes. What the diagram took from us is that clarity. It replaced the vast, dark, cold, mostly empty reality of the solar system with something manageable and organized and legible. It replaced the ocean with a puddle, and the puddle is easier to think about. It's easier to teach children about. It fits on a wall poster and in a school budget and in a 40-minute class period. But living in the puddle is not the same as living in the ocean, and the solar system is an ocean. The next time you see a graphic of the solar system, planets arranged in their familiar order, everything visible, everything scaled to fit the screen, try to remember what's missing from the image. Try to remember what was removed to make it fit. What was compressed and flattened and brought close until it looked like a place you could navigate in an afternoon, if the roads were long enough. What's missing is the dominant feature of the solar system. What's missing is the darkness between the worlds. What's missing is the months of interplanetary void between Earth and Mars, the 5 years of spacecraft travel between Earth and Jupiter, the 4-hour radio delay to Neptune, the 47 years of Voyager's travel through a solar system that's still not done with it yet. What's missing is the scale. The picture was compressed. The truth was too large to fit. That truth is this: the solar system is not a neighborhood. The planets are not close. The distances are not comfortable. And the place we call home, the 1 star and 8 worlds we have the enormous fortune of being born into, is vast beyond any honest representation on any image, dark beyond the threshold of our intuition, and mostly, overwhelmingly, humblingly empty. The emptiness is not a failure of the solar system. It is the solar system. And somewhere in that emptiness, moving at the speed of light, is the signal from every spacecraft we've ever sent to explore it, taking minutes and hours and days to return, delayed by distances the diagram never showed, crossing a void the poster never admitted existed. If this video changed something in the way the solar system feels to you, if the planets seem a little farther apart now, the distances a little less manageable, the darkness between them a little more real, that's what Novarium is here for. Subscribe if you want to keep going. There's more to see, and it doesn't get any smaller.